Let yourself settle in now. Find that place of comfort where your body can truly rest, where the concerns of the day begin to fade like distant echoes. Take a slow, deep breath, feeling the air fill your lungs, and as you release it, let the tension flow out of you like water finding its way downhill. Tonight, we're embarking on a journey through discoveries so profound they've challenged our understanding of the cosmos itself. Don't worry about remembering every detail or grasping every concept. Just let the words wash over you, painting pictures in your mind of distant galaxies, ancient stars, and worlds that might harbor life. This is a story about the most powerful telescope humanity has ever built, and the astonishing revelations it brought us when it finally opened its golden eyes to the universe. So, breathe, relax, and let's drift together into the depths of space, where the James Webb Space Telescope has shown us that reality is stranger and more beautiful than we ever imagined. Introduction. A new window opens. On Christmas morning 2021, while children across parts of the world unwrapped presents and families gathered for holiday celebrations, a different kind of gift was being prepared for all of humanity. In the humid tropical air of French Guiana on the northeastern coast of South America, an Ariane 5 rocket stood on its launch pad, carrying the most expensive, most complex, and most powerful space telescope ever constructed. The James Webb Space Telescope, folded like an enormous piece of cosmic origami to fit inside the rocket's nose cone, represented more than 20 years of development, the combined efforts of thousands of engineers and scientists, and an investment of $10 billion. It was humanity's next great eye on the universe, designed to see farther into space and deeper into time than any telescope before it. At 7:20 a.m. local time, the rocket's engines ignited with a roar that echoed across the jungle and out over the Atlantic Ocean. Slowly at first, then, with gathering speed, the Ariane 5 lifted the James Webb Space Telescope away from Earth, carrying it toward a destiny that would reshape our understanding of the cosmos. The telescope was not heading into orbit around Earth, as the Hubble Space Telescope had done 3 decades earlier. Instead, it was bound for a special location in space called the Second Lagrange Point, or L2, a gravitationally stable spot about 1 million miles from Earth in the direction away from the Sun. From that distant vantage point, Webb would have an unobstructed view of the universe, free from the heat and light of both the Sun and Earth that could interfere with its incredibly sensitive infrared detectors. But first, it had to get there in one piece, and that meant successfully completing the most complex deployment sequence ever attempted in space. Over the following month, as the telescope cruised toward its destination, engineers on Earth held their collective breath as, step by careful step, the spacecraft unfolded itself. The enormous sun shield, about the size of a tennis court when fully deployed, extended its 5 layers of material thinner than a human hair. The secondary mirror swung into position, and finally, in what seemed like an almost impossibly delicate operation, the primary mirror's 2 side panels rotated out to create the iconic hexagonal shape that would become the telescope's signature silhouette. Each step was a potential point of failure. Any one of hundreds of mechanisms could have jammed, any of dozens of motors could have failed, and the entire mission would have been compromised. But step by step, with methodical precision, the telescope unfolded exactly as planned. By mid-January 2022, Webb had reached its destination at L2 and was fully deployed. Then came months of careful calibration. The 18 hexagonal mirror segments that together form Webb's primary mirror, each one carefully crafted from beryllium and coated with a microscopically thin layer of gold, had to be aligned with nanometer precision. Using tiny motors that could adjust each segment's position and curvature, engineers painstakingly brought all 18 pieces into alignment until they functioned as a single perfect mirror 6.5 meters across. The telescope's 4 scientific instruments underwent their own tests and calibrations. The near-infrared camera, or NIR-CAM, the near-infrared spectrograph, or NIR-SPEC, the mid-infrared instrument, or MIRI, and the near-infrared imager and slitless spectrograph, or NIRIS. Each one was checked, rechecked, and fine-tuned until it operated at peak performance. Finally, on July 11, 2022, the world got its first glimpse of what Webb could do. President Joe Biden revealed the first image during a special event at the White House. A deep field showing thousands of galaxies, some of them among the most distant ever observed. Their light stretched across more than 13 billion years of cosmic history. The next day, NASA released 4 more images: the Carina Nebula, a stellar nursery where new stars were being born; the Southern Ring Nebula, the expanding corpse of a dead star; Stephan's Quintet, a group of galaxies caught in a cosmic dance; and the atmosphere of WASP 96b, an exoplanet orbiting a distant star. The images were breathtaking, revealing details never before seen and colors representing different wavelengths of infrared light translated into the visible spectrum for our eyes to appreciate. But they were just the beginning. What Webb would discover in the months and years that followed would challenge fundamental assumptions about the universe and open entirely new questions that scientists are still working to answer. Part 1. The Universe Breakers. When galaxies appeared too soon. In the first weeks and months after Webb began its scientific operations, one particular type of observation dominated much of the telescope's schedule. Astronomers call it deep field imaging, pointing the telescope at seemingly empty patches of sky and collecting light for hours or even days, allowing the faintest and most distant objects to gradually accumulate enough photons to become visible. These observations had a specific purpose. Scientists wanted to push back the cosmic frontier, to see galaxies from the earliest possible epochs of the universe's history. The Big Bang occurred 13.8 billion years ago, and for the first few hundred million years, the universe was shrouded in what astronomers call the cosmic dark ages. During this time, the universe was filled with neutral hydrogen gas that absorbed most light, making it opaque to observation. Only when the first stars and galaxies formed and began emitting intense ultraviolet radiation did this fog begin to clear in a process called reionization. Webb was specifically designed to observe this crucial period, to catch the first glimmers of light from the universe's earliest galaxies, and to understand how structure first emerged from the primordial soup of matter and energy. Its infrared sensitivity was perfect for this task, because light from these extremely distant galaxies has been stretched to longer wavelengths by the expansion of space itself, shifting visible light into the infrared range where Webb can detect it. What the telescope found was simultaneously exciting and deeply puzzling. In survey after survey, Webb detected galaxies from the universe's first few hundred million years, pushing the observational frontier closer and closer to the Big Bang itself. These weren't just faint smudges either. Some of these early galaxies appeared surprisingly bright and well-formed, showing structure and organization that seemed far more advanced than theoretical models predicted for such young objects. Then came the real bombshell. A team led by astronomer Ivo Labbé identified 6 galaxies that appeared to exist just 500 to 700 million years after the Big Bang. When they analyzed the light from these galaxies and estimated their masses, the results seemed impossible. These galaxies appeared to contain almost as many stars as the Milky Way does today, which wouldn't be completed for another 13 billion years of cosmic evolution. The team nicknamed them universe breakers, because they seemed to violate everything scientists thought they understood about how galaxies form and grow. According to current models, galaxies should assemble hierarchically, starting small and gradually growing larger through mergers and the steady accumulation of gas that cools and forms new stars. This is a slow process that takes billions of years. Finding massive, mature galaxies less than a billion years after the Big Bang was like finding a full-grown oak tree sprouting from an acorn planted last week. The implications were staggering. If these observations were correct, they suggested that either our understanding of galaxy formation was fundamentally flawed, or that the standard cosmological model itself, which describes how the universe evolved from the Big Bang to the present day, needed major revision. Some scientists even suggested that the physics underlying these models might need to be reconsidered. The discovery sent ripples through the astronomical community. Papers were written proposing various exotic explanations. Maybe the early universe had far more dark matter structures than models predicted, allowing galaxies to grow faster. Maybe there were unknown processes that could convert gas into stars with incredible efficiency. Maybe physics operated differently in the early universe than it does today. But then came the careful follow-up work, and the picture began to clarify. One of the 6 original universe breakers was observed again with spectroscopy, a technique that spreads light into its component wavelengths to reveal detailed information about an object's composition, temperature, and distance. The spectroscopic observations revealed that this particular galaxy wasn't nearly as distant as initially thought. It was at a redshift of 5.6 rather than 16, meaning it existed about a billion years after the Big Bang rather than just a few hundred million years. Its light had been misleading in the initial photometric observations, which estimate distances based on how bright an object appears in different filters. This was an important reminder that extraordinary claims require extraordinary evidence. Initial distance estimates for very faint, distant galaxies based solely on their colors in different filters can be wrong. Spectroscopy provides much more reliable confirmation, but it's also more time-consuming and can only be done for one object at a time in most cases. As more spectroscopic follow-up observations were conducted, some of the other universe breakers also turned out to be not quite as distant or massive as first appeared. But intriguingly, many of them were confirmed as genuinely early and genuinely large. These weren't measurement errors. The early universe really did contain surprisingly massive, surprisingly mature galaxies. The resolution to the puzzle appears to lie not in exotic new physics, but in understanding what makes these early galaxies appear so bright. It's not necessarily that they contain as many stars as the Milky Way. Instead, several factors combine to make them look more massive than they actually are. First, many of these early galaxies appear to have undergone intense bursts of star formation, converting their available gas into stars at incredible rates. When you form lots of stars very quickly, you create lots of young, hot, massive stars that shine brilliantly in ultraviolet light. This makes the galaxy appear much brighter than it would be if the same number of stars formed gradually over billions of years. Second, Some of these early galaxies appear to host actively feeding supermassive black holes at their centers. When a black hole consumes matter, it doesn't just make that matter disappear. The infalling material forms an incredibly hot accretion disk that can outshine all the stars in the galaxy combined. This active galactic nucleus adds significantly to the total light output, making the galaxy appear more luminous and potentially leading to overestimates of its stellar mass. Third, the very nature of these early star-forming environments may have been different from what we see in the universe today. The gas from which the first stars formed contained almost no heavy elements, only the hydrogen and helium created in the Big Bang. This pristine composition may have allowed stars to form more efficiently or to grow more massive than typical stars today, further enhancing the brightness of early galaxies. While the universe breakers aren't quite as revolutionary as initially feared, they've still forced astronomers to revise their models of early galaxy formation. Galaxies in the early universe were clearly able to assemble and begin forming stars faster and more efficiently than standard models predicted. The period between the cosmic dark ages and the emergence of mature galaxies was shorter and more dynamic than previously thought. Webb continues to observe these early galaxies, gathering more data and pushing even farther back in time. In May 2024, astronomers announced the discovery of JWST, a galaxy observed just 290 million years after the Big Bang, currently the most distant confirmed galaxy known. Its light has been traveling through space for more than 13.5 billion years to reach us, showing us what the universe looked like when it was barely 2% of its current age. These observations are revealing the universe's adolescence, that crucial period when the first structures emerged from chaos and began the long journey toward becoming the rich, complex cosmos we see today. And, while the universe hasn't been broken by these discoveries, it's clear that it was a more precocious child than we gave it credit for, growing up faster and more dramatically than our models suggested. Part 2. Earendel, Touching the Stars of Deep Time. Among Webb's most remarkable capabilities is its ability to study not just galaxies from the early universe, but individual stars within those galaxies. This might not sound revolutionary at first. After all, telescopes have been resolving individual stars for centuries. But there's a crucial difference. Webb can see individual stars in galaxies billions of light years away, stars that lived and died when the universe was young. This capability exists thanks to a cosmic trick called gravitational lensing. Einstein's general theory of relativity tells us that massive objects warp the fabric of space-time itself. When light from a distant source passes near a massive object like a galaxy cluster, its path bends just as light bends when passing through a glass lens. If the alignment is just right, this gravitational lens can dramatically magnify the light from background objects, allowing us to see things that would otherwise be far too faint to detect. In March 2022, just as Webb was completing its commissioning phase, astronomers using the Hubble Space Telescope announced a stunning discovery. They had detected an individual star, magnified by a factor of several thousand by a massive galaxy cluster called WHL 013708, that existed when the universe was less than 1 billion years old. The discovery team nicknamed this star Earendel, from the Old English word meaning morning star or rising light, a name that also carries echoes of J.R.R. Tolkien's mythology. Earendel held the record as the most distant individual star ever observed, its light having traveled 12.9 billion years to reach us. The star existed when the universe was only 900 million years old, just 7% of its current age. But Hubble, observing primarily in visible and near ultraviolet wavelengths, could only tell astronomers so much about this ancient star. Enter James Webb. One of Webb's early observation programs was designed to follow up on Hubble's discovery of Earendel, using the telescope's infrared capabilities to learn more about this remarkable object. In July 2022, just days after beginning science operations, Webb pointed its mirrors toward the galaxy cluster WHL 0137 Urido-8 and the gravitationally lensed galaxy behind it, known as the Sunrise Arc, due to its elongated arc-like shape caused by lensing. The observations were successful. Webb not only detected Earendel, but revealed it in far greater detail than Hubble had managed. Using its near-infrared camera, Webb captured images showing Earendel as a point of light, even with the telescope's remarkable resolving power. This told astronomers that the source must be very small, smaller than about 4,000 astronomical units across. For comparison, that's about 100 times the distance from the Sun to Earth, which sounds large but is actually tiny on cosmic scales. More importantly, Webb's instruments could analyze Earendel's light to determine its properties. By spreading the starlight into a spectrum and analyzing which wavelengths were present and which were absorbed, astronomers could determine the star's temperature and composition. The results painted a portrait of an extraordinary object. Earendel appeared to be what astronomers call a B-type star, a classification based on its spectral characteristics. B-type stars are massive, hot, and luminous. Based on Webb's observations, Earendel was determined to have a surface temperature more than twice that of our Sun, somewhere between 13,000 and 16,000 Kelvin. Our Sun, by comparison, has a surface temperature of only about 5,700 Kelvin. The star's luminosity, its total light output, was estimated at roughly 1,000,000 times that of our Sun. This made Earendel an absolute beacon, a cosmic lighthouse shining across billions of light years and billions of years of time. Even with the magnification provided by gravitational lensing, detecting such an object is a testament to both nature's helpful lens and human technological achievement. But Webb revealed something else intriguing. When astronomers analyzed the full spectrum of light from Earendel, they found hints of something unexpected, the possible presence of a companion star. The colors of light suggested that in addition to the bright, hot primary star, there might be a cooler, redder companion orbiting nearby. This wouldn't be surprising if confirmed. Most massive stars, like Earendel, exist in binary or multiple star systems, gravitationally bound to one or more stellar siblings. The light from this potential companion had been stretched by the universe's expansion into longer wavelengths that Hubble couldn't detect, which is why it hadn't been seen in the original discovery observations. But Webb, with its infrared sensitivity, could pick up these longer wavelengths and reveal the companion's presence. This discovery of a potential binary system, 900 million years after the Big Bang, provides valuable insights into the early universe. It suggests that even in those ancient times, stars formed and evolved in ways similar to what we see today. Binary systems weren't just a feature of the mature universe. They existed from nearly the beginning. However, the story of Earendel took an interesting turn in 2025. Additional observations and more detailed analysis by a team led by Massimo Pascal suggested that Earendel might not be a single star or even a binary system at all. Instead, it could be a compact star cluster, a group of perhaps dozens or hundreds of stars bound together by gravity and formed from the same cloud of gas. This reinterpretation came from carefully analyzing Earendel's spectrum and comparing it to the spectra of known single stars and star clusters. The researchers found that the spectral features of Earendel could be better explained by a collection of many stars rather than one or two individual stars. The object's size, while remarkably small for a star cluster at less than a parsec across, was consistent with this interpretation. If Earendel is indeed a star cluster rather than a single star, it would represent a precursor to the globular clusters we see in the universe today. Globular clusters are ancient, tightly packed collections of hundreds of thousands of stars that orbit galaxies. They're thought to have formed in the early universe, and Earendel might be catching one in the act of formation. This doesn't diminish the significance of the discovery. Whether Earendel is one star, two stars, or a cluster of stars, it remains a remarkable window into the early universe. It shows us that just 900 million years after the Big Bang, when the universe was still in its infancy, stars were already shining brightly enough to be detected across cosmic distances with the right combination of gravitational lensing and sensitive instruments. The debate over Earendel's true nature highlights an important aspect of science. Discovery is a process, not an event. Initial observations and interpretations can be refined and even overturned as more data becomes available and more sophisticated analysis techniques are applied. What matters is that Webb has given us the ability to study individual stellar objects from the early universe, whether they're single stars or star clusters, and to test our theories about how these first luminous objects formed and evolved. Webb has since detected other distant stars using gravitational lensing, though none quite as far as Earendel. Each discovery adds to our growing understanding of stellar populations in the early universe, and helps us piece together the story of how the cosmos transitioned from darkness to light during those critical first billion years. Part 3. The Hubble Tension. A crisis confirmed. Among the most important questions in cosmology is one that sounds deceptively simple. How fast is the universe expanding? This expansion rate, called the Hubble constant after Edwin Hubble, who first discovered that the universe was expanding, is a fundamental parameter that's connected to the universe's age, its composition, and its ultimate fate. For decades, astronomers have worked to measure the Hubble constant with ever greater precision, and for a while, it seemed like the measurements were converging toward a consistent answer. But then, about a decade ago, a troubling discrepancy emerged. Different methods for measuring the Hubble constant were giving slightly different answers, and the differences were too large to be explained by random measurement errors. This problem became known as the Hubble tension, and it's one of the biggest puzzles in modern cosmology. On one side are measurements based on observations of the early universe, particularly the cosmic microwave background radiation, the ancient light from when the universe was only 380,000 years old. These observations, combined with our standard model of cosmology, predict a Hubble constant of about 67 kilometers per second per megaparsec. On the other side are measurements based on observations of the nearby modern universe. One particularly important technique uses a type of variable star called Cepheids as cosmic distance markers. Cepheid variables pulsate with periods directly related to their intrinsic brightness, which means by measuring how fast a Cepheid pulsates, you can determine how bright it actually is. Comparing this intrinsic brightness to how bright it appears gives you its distance. By measuring distances to galaxies this way and comparing them to how fast those galaxies are receding from us, you can calculate the expansion rate. Measurements using Cepheids and other local universe methods have consistently given a Hubble constant of about 73 kilometers per second per megaparsec, significantly higher than the early universe measurements predict. The difference might not sound like much, but in cosmology, it's huge. It's statistically significant, meaning it can't be explained away as a fluke or measurement error. And it suggests that either something is wrong with our measurements or something is wrong with our understanding of how the universe works. Many solutions have been proposed. Maybe there are subtle systematic errors in one or both measurement techniques. Maybe the cosmic microwave background is being influenced by physics we don't fully understand. Maybe there's some exotic form of dark energy or dark matter that affects the expansion rate in ways we haven't accounted for. Maybe the fundamental laws of physics evolved over cosmic time. Enter James Webb, with its unprecedented ability to observe Cepheid variable stars in distant galaxies with remarkable clarity. Adam Riess, who won the Nobel Prize in Physics in 2011 for the discovery that the universe's expansion is accelerating, led a team that used Webb to observe Cepheids in galaxies out to distances where Hubble was struggling to distinguish individual stars. Webb's larger mirror and sharper vision allowed it to resolve Cepheids that Hubble could only barely detect, reducing the uncertainty in distance measurements. The question was, would Webb's more precise observations resolve the Hubble tension by showing that one set of measurements had been wrong? Or would it confirm that the tension was real? Unfortunately, for those hoping for a simple resolution, Webb confirmed the tension. The new observations, combining Webb's data with Hubble's measurements, yielded a Hubble constant consistent with the higher value from local universe observations. The discrepancy with early universe measurements remained. This is not the answer astronomers wanted, but in some ways it's the most interesting possible result. If the measurements had converged, it would have meant one technique was flawed, and the problem could be fixed. But with Webb confirming the discrepancy, it suggests we're facing something more profound. Either there's something systematically wrong with how we're measuring the early universe parameters, or there's new physics at play that we don't yet understand. The confirmation of the Hubble tension has sparked intense theoretical work. Physicists are exploring models where dark energy, the mysterious force causing the universe's expansion to accelerate, behaves differently than we've assumed. Others are investigating whether the universe has properties that vary from place to place, rather than being perfectly uniform. Still others are revisiting fundamental assumptions about how the cosmic microwave background should be interpreted. This is how science advances. Sometimes better measurements don't solve problems but deepen them, forcing us to question assumptions we thought were solid. The Hubble tension remains one of the most important unsolved problems in cosmology, and Webb's contribution has been to show us that the problem is real and demands a solution. Whatever that solution turns out to be, it will likely reshape our understanding of the cosmos in profound ways. Part 4, K2 to 18b. The Controversial Search for Life. One of Webb's most anticipated capabilities was its ability to study the atmospheres of exoplanets, planets orbiting stars other than our Sun. By observing an exoplanet as it passes in front of its star, Webb can detect the tiny fraction of starlight that filters through the planet's atmosphere. Different gases in the atmosphere absorb light at specific wavelengths, leaving telltale fingerprints in the star's spectrum that reveal what the planet's air contains. This technique, called transmission spectroscopy, opens up the possibility of detecting biosignatures, chemical compounds that might indicate the presence of life. On Earth, for instance, oxygen and methane coexist in the atmosphere in a state far from chemical equilibrium, maintained only by the constant activity of living organisms. Finding a similar chemical imbalance on an exoplanet could be a sign that life exists there too. In 2023, a team led by Niku Madhusudan at the University of Cambridge announced exciting results from Webb observations of an exoplanet called K2-SU-18b. This world, located about 124 light-years away in the constellation Leo, is what's known as a sub-Neptune, a planet between Earth and Neptune in size. K2-18b is about 8.6 times Earth's mass and 2.6 times Earth's radius, placing it in a poorly understood category of planets that don't exist in our own solar system. What makes K2-18b particularly interesting is its location. The planet orbits within its star's habitable zone, the region where temperatures could potentially allow liquid water to exist on a planetary surface. K2-18b's parent star is a cool red dwarf, much smaller and dimmer than our Sun, which means the habitable zone is much closer to the star. K2-18b completes an orbit every 33 days, receiving about as much energy from its star as Earth receives from the Sun. The initial Webb observations, using the telescope's near-infrared spectrograph and near-infrared imager and slitless spectrograph, detected methane and carbon dioxide in K2-18b's atmosphere. This was already a significant finding, as it was the first time carbon-based molecules had been detected in the atmosphere of an exoplanet in the habitable zone. The results were consistent with K2-18b being what the team called a Hycean world, a hypothetical type of planet with a global ocean beneath a hydrogen-rich atmosphere. But there was something else in the data, a weaker signal that hinted at the presence of dimethyl sulfide, or DMS. This molecule is particularly intriguing because on Earth, DMS is produced almost exclusively by biological processes, specifically by marine microorganisms like phytoplankton. Finding DMS on another world could potentially be evidence of alien life. The team was appropriately cautious about this detection. The signal was weak, reaching only about 2 sigma statistical significance, meaning there was roughly a 5% chance it could be a random fluctuation rather than a real detection. The scientific gold standard for discovery is 5 sigma, which corresponds to only a 0.006% probability of being a false positive. The DMS hint was intriguing but far from conclusive. In April 2025, the same team announced new results based on additional Webb observations using a different instrument, the Mid-Infrared Instrument, or MIRI. These observations strengthened the case for DMS, or a closely related molecule called dimethyl disulfide, bringing the detection up to 3 sigma significance, a 0.3% probability of being a chance fluctuation. Still not 5 sigma, but much more robust than before. The concentrations of DMS indicated by these observations were remarkable. On Earth, DMS exists in the atmosphere at levels below 1 part per billion by volume. On K2-18b, if the detection is real, DMS would be present at levels thousands of times higher, more than 10 parts per million. The team suggested that 16 to 24 additional hours of observation time with Webb might be enough to push the detection to 5 sigma and confirm the presence of this potential biosignature. However, the scientific community remains divided on how to interpret these results. While the DMS detection has strengthened with additional observations, significant questions remain about whether it's really there and what it would mean if it is. In summer 2025, a NASA-led team conducted an independent reanalysis of the Webb data using more sophisticated statistical methods. Their analysis, which hasn't yet been peer-reviewed but was uploaded to the Archaeology preprint server in July, came to more cautious conclusions. While they confirmed the presence of water vapor, methane, and carbon dioxide in K2-18b's atmosphere, they found no conclusive evidence for DMS. The signal was present in the data, but fell below the threshold for definitive confirmation. This doesn't necessarily mean DMS isn't there. It means the current data, even with Webb's remarkable capabilities, isn't quite good enough to be certain. The reanalysis also highlighted how different analytical approaches can yield different conclusions from the same data, emphasizing the importance of independent verification and the need for even more observations. Beyond the question of whether DMS is really present, there's the question of what it would mean if it is. On Earth, yes, DMS is produced by life. But Earth is the only planet with life we know about, which makes it a sample size of one. We can't be sure that DMS is a universal biosignature. There could be abiotic processes, chemical reactions that don't involve life, that produce DMS under conditions very different from Earth. In fact, there's already evidence for this. In 2015, the European Space Agency's Rosetta spacecraft detected DMS in the coma of Comet 67P Churyumov-Gerasimenko, a chunk of ice and rock that certainly doesn't host life. This suggests that DMS can be produced by non-biological processes, at least in some environments. Furthermore, K2-18b's atmosphere is very different from Earth's. It's dominated by hydrogen rather than nitrogen and oxygen, and the planet itself, being so much larger than Earth, likely has a very different internal structure and surface conditions. Chemical processes that don't occur on Earth might be commonplace on K2-18b, potentially producing DMS without any biological involvement. Some researchers have also questioned whether K2-18b could host life at all. While it orbits in the habitable zone, that just means it receives an amount of energy that could allow liquid water under the right conditions. But K2-18b might not have the right conditions. It could be more like a mini Neptune, with a deep atmosphere and no solid surface at all, rather than a Hycean world with an ocean. If the planet's hydrogen atmosphere is too thick and extends too deep, the pressure and temperature at lower levels would be far too extreme for any life we can imagine. The controversy surrounding K2-18b illustrates both the promise and the challenges of using Webb to search for biosignatures. The telescope has the sensitivity to detect molecules in exoplanet atmospheres that previous instruments couldn't. But detecting a molecule is one thing. Understanding what that detection means, distinguishing between biological and non-biological origins, and confirming that the detection is real rather than an artifact of noise or analysis choices, all require careful work and often additional observations. NASA emphasized this in a statement about the K2-18b findings, noting that detecting a single potential biosignature would not constitute discovery of life. Multiple converging lines of evidence would be needed, possibly including independent data from multiple missions. The team that made the DMS detection is requesting more observation time with Webb to improve the statistics and potentially reach the 5 sigma threshold. Other teams are planning observations of K2-18b and similar planets using different techniques and instruments. The debate will continue, and more data will gradually clarify whether DMS is really present and what it means. Regardless of how the K2-18b story ultimately resolves, It's demonstrated that we've entered a new era in the search for life beyond Earth. For the first time, we have the technology to detect potential biosignature gases in the atmospheres of exoplanets. We're asking questions that a generation ago would have been pure speculation. And whether or not K218b harbors life, it's certain that Webb and future telescopes will continue searching, examining the atmospheres of dozens or hundreds of worlds, looking for the chemical fingerprints that might indicate we're not alone in the universe. Part 5. Dark Stars. A Speculative Glimpse. Among the more speculative but fascinating discoveries from Webb's early observations was the possible detection of what some scientists call dark stars. These aren't stars made of ordinary matter shining through nuclear fusion like our Sun. Instead, they would be powered by the annihilation of dark matter particles colliding and destroying each other in the star's core. Dark matter is one of the great mysteries of modern physics. Approximately 85% of all matter in the universe doesn't emit, absorb, or reflect light. We know it exists because we can see its gravitational effects on visible matter and on light passing through space. Without dark matter, galaxies would fly apart. Without dark matter, the universe's large-scale structure wouldn't have formed the way it did. But we don't know what dark matter actually is. We've never detected a dark matter particle directly. One theoretical possibility is that dark matter consists of particles called weakly interacting massive particles, or WIMPs. These hypothetical particles would rarely interact with ordinary matter, which is why we haven't detected them yet. But they could interact with each other. When two WIMPs collide, they could annihilate, converting their mass into energy according to Einstein's famous equation, E and mmc2. If enough dark matter collected in a dense clump, like the core of a forming star, these annihilations could produce enormous amounts of energy. Theoretical physicist Catherine Freese and her colleagues have proposed that, in the early universe, dark matter annihilation could have powered the first stars. These dark stars would have been enormous, potentially thousands of times larger than the Sun, and incredibly luminous, but they would have shone not from nuclear fusion, but from dark matter destruction. In 2023, Freese and her team announced that Webb might have detected 3 objects that could be dark stars. These objects had originally been identified as early galaxies in Webb's deep field observations. But when Freese's team analyzed their properties, they found that the objects could also be explained as individual dark stars. The key was that these objects appeared extremely bright for their presumed distances and ages. If they were galaxies, they would need to contain millions of ordinary stars, which would be challenging to form so quickly in the early universe. But if they were dark stars, a single object could produce enough light to match what Webb observed. As Freese explained, there were 2 competing possibilities. Either these objects were galaxies containing millions of ordinary population 3 stars, the first generation of stars made purely from hydrogen and helium. Or they were dark stars, enormous stellar objects powered by dark matter annihilation. Remarkably, one dark star could produce enough light to rival an entire galaxy's worth of ordinary stars. The hypothesis is tantalizing, because dark stars would solve several puzzles about the early universe. They could help explain how supermassive black holes, which we see at the centers of galaxies very early in cosmic history, grew so large so quickly. A dark star, which could be millions of times more massive than the Sun, would eventually collapse into a massive black hole when the dark matter fuel ran out, providing a seed for the supermassive black holes we observe. However, the dark star interpretation remains highly speculative and controversial. Most astronomers think these objects are more likely to be early galaxies, or perhaps galaxies with unusually active, supermassive black holes at their centers. The extraordinary claim that they're powered by dark matter would require extraordinary evidence, and that evidence doesn't yet exist. To confirm the dark star hypothesis would require detecting specific spectral signatures that distinguish dark matter annihilation from ordinary stellar fusion or black hole accretion. Webb's observations show interesting properties, but haven't yet provided the smoking gun evidence that would prove dark stars exist. More observations are planned, and whether these mysterious objects turn out to be galaxies, dark stars, or something else entirely, they represent one of the most intriguing mysteries Webb has uncovered. Part 6. The Cosmic Dawn. Reionization Revealed. One of Webb's primary science goals was to study the epoch of reionization, the period when the universe transformed from being opaque to transparent. Understanding this transformation is crucial to understanding how the universe evolved from the Big Bang to the cosmos we see today. For the first 380,000 years after the Big Bang, the universe was so hot that electrons couldn't stay attached to atomic nuclei. Matter existed as a plasma, a hot soup of charged particles. Photons, particles of light, couldn't travel far in this plasma because they constantly scattered off free electrons. The universe was opaque, foggy, impenetrable to observation. Then, as the universe expanded and cooled, it reached a temperature where electrons could finally attach to nuclei, forming neutral atoms, primarily hydrogen and helium. This moment, called recombination, released the cosmic microwave background radiation that Webb's predecessors have studied in such detail. With electrons bound into atoms, light could suddenly travel freely. The fog cleared, at least temporarily, but the universe entered a new dark age. With no stars yet shining, no galaxies yet glowing, space was filled with neutral hydrogen gas that absorbed ultraviolet light. The universe was transparent to some wavelengths, but opaque to others, and it would remain this way for tens or hundreds of millions of years until the first stars ignited. When those first stars finally turned on, they began emitting intense ultraviolet radiation. This high-energy light had enough energy to ionize hydrogen atoms, splitting them back into protons and electrons. Around each star, a bubble of ionized gas began to grow, expanding outward as the star's ultraviolet photons ionized more and more hydrogen. As more stars formed, more bubbles appeared. Eventually, these bubbles overlapped and merged, and the universe became reionized, filled with ionized hydrogen that allowed ultraviolet light to travel freely. This process, the epoch of reionization, fundamentally changed the universe. It determined how subsequent generations of stars and galaxies would form. It influenced the large-scale distribution of matter. Understanding when and how it occurred is essential to understanding cosmic history. Webb's observations have begun to reveal the details of this crucial epoch. By detecting galaxies from when the universe was just a few 100 million years old, Webb is catching the first light sources that drove reionization. The telescope can observe how these early galaxies were distributed, how quickly they were forming stars, and how much ultraviolet light they were producing. One key discovery is that early galaxies were forming stars at much higher rates than previously expected. Many of the galaxies Webb has detected from the first billion years show signs of vigorous star formation, converting their gas into stars at rates that would deplete their fuel in relatively short cosmic timescales. This intense star formation would have produced copious amounts of ultraviolet radiation, helping to reionize the universe faster than some models predicted. Webb has also detected what appear to be some of the earliest examples of active galactic nuclei, supermassive black holes actively consuming matter. These objects produce even more ultraviolet and X-ray radiation than stars, and they may have played an important role in Reionization alongside stellar sources. Surveys conducted with Webb have found that galaxies in the early universe were surprisingly numerous. There were more galaxies forming earlier than many models predicted. This abundance of early galaxies means there were more sources of ionizing radiation than expected, which has important implications for understanding how quickly reionization proceeded. The telescope has also begun to detect what are called Lyman alpha emitters, galaxies that show strong emission from hydrogen gas being ionized by ultraviolet light. By mapping where these galaxies are and aren't present, astronomers can trace the boundaries of ionized regions and watch how they grew and merged over cosmic time. All of this paints a picture of reionization as a complex, patchy process. It didn't happen uniformly across the universe. Instead, ionized bubbles appeared around the first light sources, grew, merged, and eventually filled space. The process likely took several hundred million years, from perhaps 150 million to about 1 billion years after the Big Bang, though the exact timeline is still being refined as Webb gathers more data. Understanding reionization isn't just about satisfying cosmic curiosity. The epoch of reionization affected how galaxies formed and evolved. It influenced which regions of space would become dense with galaxies and which would remain relatively empty. It determined the temperature and state of the gas that would feed subsequent generations of star formation. By studying reionization with Webb, astronomers are learning how the universe transformed from a simple, mostly uniform state after the Big Bang into the complex, structured cosmos we inhabit today. Part 7. Stellar Nurseries Unveiled. Among Webb's most visually stunning achievements are its observations of star-forming regions, the cosmic nurseries where new stars are born from clouds of gas and dust. These regions, also called nebulae, have been photographed many times before by telescopes like Hubble. But Webb's infrared vision reveals them in entirely new ways, penetrating the dust that obscures visible light and exposing the hidden architecture of stellar birth. One of the first images released during Webb's initial data release in July 2022 was the Carina Nebula, a massive star-forming region located about 7,600 light-years away in the southern constellation Carina. The image showed towering pillars of gas and dust, illuminated and sculpted by radiation from nearby massive stars. The scene resembled a cosmic landscape of mountains and valleys, with young stars glittering like jewels against the darkness. But this was more than just a pretty picture. By observing in infrared wavelengths, Webb could see through the dust clouds to reveal stars that had only recently ignited, still embedded in their natal cocoons of gas. These protostars, invisible to Hubble's cameras, showed up clearly in Webb's images, along with the jets of material they were ejecting and the shock waves those jets created as they plowed into surrounding gas. Webb's observations of the Carina Nebula and other star-forming regions have revealed the process of star formation in unprecedented detail. Astronomers can see individual protostars at different stages of development, from dense clumps of gas just beginning to collapse under their own gravity. to more evolved objects that have already ignited nuclear fusion in their cores and are beginning to clear away their surrounding material. The telescope has also revealed the fine structure of protoplanetary disks, the flattened clouds of gas and dust surrounding young stars where planets form. By resolving these disks and analyzing their composition, astronomers can study the raw materials from which planetary systems are built. Webb has detected water ice, organic molecules, and other compounds in these disks, providing insights into the chemical inventory available for planet formation. In some star-forming regions, Webb has observed what are called proplyds, protoplanetary disks that are being eroded and evaporated by intense radiation from nearby massive stars. These observations show how the environment influences planet formation. In regions where massive stars have formed, their intense radiation can destroy or truncate the protoplanetary disks around smaller stars, potentially preventing those stars from forming large planetary systems. Webb has also studied more exotic star-forming environments. Observations of the Tarantula Nebula in the Large Magellanic Cloud, a nearby dwarf galaxy, revealed thousands of young stars that had never been seen before, along with distant background galaxies, visible through gaps in the nebula's dusty structure. The Tarantula Nebula is one of the most active star-forming regions in the nearby universe, producing stars at a rate far higher than anything in our own Milky Way galaxy. By comparing star-forming regions in different galaxies and at different cosmic epochs, astronomers can study how star formation has evolved over the history of the universe. The chemical composition of gas clouds has changed over time as successive generations of stars have synthesized heavier elements and distributed them through supernova explosions. Webb's observations are revealing how this chemical enrichment has affected the star formation process and the types of stars that form. One particularly important question is whether the star formation process is universal or whether it changes under different conditions. Do stars form the same way in low metallicity gas clouds, like those in the early universe, as they do in metal-rich clouds like those in the modern Milky Way? Webb's observations of both early galaxies and nearby star-forming regions are helping to answer this question, revealing both similarities and differences that constrain our theoretical models. Part 8. Supernova Archaeology. Among the most dramatic events in the universe are supernovae, the explosive deaths of massive stars. These cosmic detonations can briefly outshine entire galaxies, releasing in seconds as much energy as the Sun will produce over its entire 10 billion-year lifetime. Supernovae are responsible for creating and distributing many of the heavy elements essential for life, including the calcium in your bones, the iron in your blood, and the oxygen you breathe. Webb has turned its attention to several historically significant supernovae, studying their remnants to understand the explosion mechanisms and the evolution of these cosmic debris fields. One of the telescope's most remarkable observations was of supernova 1987A, the closest supernova visible to the naked eye since 1604, which occurred in the Large Magellanic Cloud, about 168,000 light-years away. When SN 1987A exploded, astronomers around the world rushed to observe it, with every available instrument. The supernova provided unprecedented insights into how massive stars die, confirming theoretical predictions about neutrino emission and shockwave propagation. In the decades since, the expanding debris from the explosion has provided a laboratory for studying how supernova remnants evolve and interact with their surroundings. Webb's observations of SN 1987A revealed remarkable new structures within the expanding debris field. The telescope detected bright spots of emission that appeared to be clumps of material from the exploded star, now being heated by shock waves as they collide with gas ejected from the star before it exploded. These observations are helping astronomers understand how the material from supernovae mixes and disperses into space, eventually becoming part of new generations of stars and planets. Webb has also studied the remnants of much older supernovae, including the famous Crab Nebula, the remains of a supernova observed by Chinese astronomers in 1054 CE. By observing these older remnants in infrared wavelengths, Webb can see through the visible light emission to detect cooler dust and molecular gas within the debris, revealing aspects of the remnants' structure and composition that visible light observations miss. One particularly significant discovery was Webb's detection of dust within supernova remnants. Theoretical models have long predicted that supernova should be important sites of dust formation, where atoms from the explosion cool and condense into solid particles. But previous observations had struggled to detect large amounts of dust in young supernova remnants. Webb's infrared sensitivity has finally confirmed that substantial quantities of dust do indeed form in these environments, validating theoretical predictions and helping to solve the puzzle of where dust in the early universe came from. In the earliest galaxies that Webb has observed, astronomers have detected significant amounts of dust. This was initially puzzling because dust grains are made of heavy elements that must first be synthesized in stars and distributed by supernovae. How did so much dust appear so quickly in the early universe? Webb's confirmation that supernovae produce substantial amounts of dust helps answer this question, showing that these explosions could have enriched the early universe with both heavy elements and dust grains within a few 100 million years of the first stars forming. Part 9. Planetary Science at the Edge. While much of Webb's attention has focused on distant galaxies and the early universe, the telescope has also made significant contributions to planetary science, studying objects within our own solar system and planets orbiting nearby stars. One remarkable observation involved Jupiter, our solar system's largest planet. Webb detected features above Jupiter's famous Great Red Spot that had never been seen before. Using the telescope's near-infrared spectrograph, astronomers observed infrared light coming from high in Jupiter's atmosphere above the storm system. This revealed complex atmospheric structure and dynamics that weren't visible in previous observations. The telescope has also observed Saturn, capturing detailed images of the planet's rings in infrared light. These observations revealed subtle structures in the rings and detected seasonal changes in Saturn's atmosphere, including unusual features near the planet's poles. Webb has studied objects in the outer solar system, including the ice giants Uranus and Neptune, and trans-Neptunian objects like dwarf planets and comets. Observations of Uranus revealed its faint rings and several of its moons with remarkable clarity. The planet itself appeared as a serene blue-green orb with subtle atmospheric features, quite different from its appearance in visible light. One unexpected discovery came in late 2024, when Webb observations led to the identification of a previously unknown moon orbiting Uranus, bringing the planet's known satellite count to 29. The moon was detected through careful analysis of Webb's high-resolution images, demonstrating that even well-studied bodies in our solar system can still hold surprises. Webb has also conducted groundbreaking observations of asteroids. In late 2024 and early 2025, the telescope observed asteroid 2024 YR4, an object that, when discovered, raised concerns about a potential impact with Earth. Webb's observations helped refine the asteroid's orbit and confirmed that it posed no significant threat, while also providing detailed information about the asteroid's composition and size. Perhaps most excitingly, Webb has studied the atmospheres of exoplanets, planets orbiting stars beyond our solar system. The telescope has detected atmospheric compositions for dozens of exoplanets, ranging from hot Jupiters, massive gas giants orbiting very close to their stars, to smaller Neptune-like and possibly rocky worlds. One of Webb's first exoplanet observations was of WASP 96b, a hot Jupiter located about 1,000 light-years away. The telescope detected water vapor, clouds, and haze in the planet's atmosphere with unprecedented detail. This observation demonstrated Webb's capability to characterize exoplanet atmospheres and set the stage for more detailed studies. The telescope has since observed exoplanets of various sizes and types, building up a catalog of atmospheric compositions that's helping astronomers understand how planets form and evolve under different conditions. Some hot Jupiters show evidence of exotic chemical processes, with temperatures so high that clouds might be made of silicate particles rather than water droplets. Other worlds show surprising amounts of methane, carbon dioxide, or other molecules that provide clues about their formation histories. One particularly intriguing observation involved an exoplanet called PSR J2322-2650b, which orbits not an ordinary star but a pulsar, a rapidly spinning neutron star. This exotic world, subject to intense radiation from its pulsar companion, represents an entirely different category of planetary environment than anything in our own solar system. Webb's observations are beginning to reveal what conditions might be like on such a world. Part 10. Brown Dwarfs Beyond the Milky Way. An particularly unexpected achievement came in late 2024, when Webb detected the first population of brown dwarf candidates outside our own Milky Way galaxy. Brown dwarfs are fascinating objects that fall into the gap between the largest planets and the smallest stars. They're more massive than planets, but not massive enough to sustain hydrogen fusion in their cores, the process that powers ordinary stars. They glow dimly from the heat of their formation and gravitational contraction, gradually cooling and fading over billions of years. In our own galaxy, thousands of brown dwarfs have been discovered, often lurking in the solar neighborhood as faint, cool objects invisible to most surveys. But detecting brown dwarfs in other galaxies seemed nearly impossible. Even relatively nearby galaxies are millions of light-years away, and brown dwarfs are intrinsically so faint that picking them out at such distances would require extraordinary sensitivity and resolution. The breakthrough came from observations of the star cluster NGC 602, located in the small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way at a distance of about 200,000 light-years. This is still technically extragalactic, beyond our own galaxy's boundaries, making any brown dwarfs detected there the first known outside the Milky Way. Webb's observations of NGC 602 revealed a rich population of cool, faint objects that have the properties expected for brown dwarfs. The cluster is young, only about 3 million years old, which means any brown dwarfs that formed with the cluster's stars should still be relatively warm and luminous compared to older brown dwarfs. Webb's infrared sensitivity was perfectly suited to detecting these objects. The discovery is significant for several reasons. First, it demonstrates Webb's incredible capability to detect faint objects at cosmological distances. Second, it provides a test case for theories of brown dwarf formation. The Small Magellanic Cloud has a much lower abundance of heavy elements than the Milky Way, which may affect how stars and brown dwarfs form. By studying brown dwarfs in this low metallicity environment, astronomers can test whether the formation process is universal or depends on chemical composition. Third, the discovery opens up the possibility of studying brown dwarfs in a variety of galactic environments, comparing formation and evolution in different contexts. Over time, as Webb accumulates more observations, astronomers may build up samples of brown dwarfs from multiple galaxies, each with different properties, providing a comprehensive view of these mysterious objects across cosmic history. Part 11. The Deepening Mystery of Dark Matter. Webb's observations have also contributed to our understanding, or perhaps more accurately, our recognition of our lack of understanding of dark matter. This invisible substance makes up 85% of all matter in the universe, yet we still don't know what it's made of or how it behaves beyond its gravitational effects. Observations of gravitational lensing, where the gravity of massive objects like galaxy clusters bends light from more distant sources, have provided some of the strongest evidence for dark matter's existence. Webb has captured numerous examples of gravitational lensing with unprecedented clarity, allowing astronomers to map dark matter distributions in galaxy clusters more precisely than ever before. One particularly striking image showed a galaxy cluster called Hubble 2744, sometimes called Pandora's Cluster, where the combined gravity of hundreds of galaxies and vast amounts of dark matter creates a complex gravitational lens. Background galaxies appear stretched and distorted into arcs and even complete rings, their light bent and magnified by the intervening mass. By carefully analyzing these distortions, astronomers can reconstruct where the dark matter is located and how much of it is present. These observations have revealed that dark matter distributions don't always match the distributions of visible matter. In some galaxy clusters, the dark matter appears offset from where most of the galaxies are concentrated, possibly due to collisions between clusters that separated the dark matter from the ordinary matter in complex ways. Webb's observations of early galaxies have also shed light on dark matter's role in cosmic structure formation. The current theoretical framework, called lambda-CDM cosmology, where CDM stands for cold dark matter, predicts that dark matter formed the scaffolding along which ordinary matter collected to form galaxies. Webb's detection of galaxies at extremely early times, along with their surprising masses and star formation rates, is helping to test this framework and constrain the properties dark matter must have to produce the observed universe. Some alternative theories of dark matter have suggested that it might interact with itself or with ordinary matter through forces beyond just gravity. Webb's observations, particularly of early galaxies and gravitational lensing, are beginning to constrain these alternative models, ruling out some possibilities and narrowing the range of viable dark matter properties. Part 12. Interstellar Visitor. In early 2025, Webb turned its attention to an unexpected visitor from beyond our solar system. Interstellar Object 3I Atlas, a comet that originated in another star system and was passing through ours on a trajectory that would eventually carry it back into interstellar space. This was only the third confirmed interstellar object detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. Unlike those previous visitors, 3I Atlas was detected early enough that multiple observatories, including Webb, could study it in detail before it receded into the distance. Webb's observations of 3I Atlas revealed that the comet was developing a substantial tail as it approached the Sun and began to warm up. More importantly, the telescope's spectrographic capabilities allowed astronomers to determine what the comet was made of, providing the first detailed compositional analysis of material from another star system. The observations detected water ice, as expected for a comet, but also revealed the presence of complex organic molecules and other compounds. By comparing the composition of 3I Atlas to comets native to our solar system, astronomers could search for similarities and differences that might reveal how planetary systems around other stars form and evolve. Interestingly, the comet's composition appeared broadly similar to solar system comets, suggesting that at least some aspects of planet and comet formation might be universal across different stellar environments. However, there were also subtle differences in the ratios of certain isotopes and molecules that hinted at formation under slightly different conditions than those that produced our solar system's comets. The discovery and subsequent observation of 3I Atlas highlighted one of astronomy's ongoing challenges and opportunities. Interstellar objects pass through our solar system regularly, but they're extremely difficult to detect because they're small, faint, and moving quickly. Most probably pass by unnoticed. But when we do detect them early enough to observe them carefully, they provide priceless samples of matter from other star systems, allowing us to study alien planetary systems without leaving our own cosmic neighborhood. Webb's ability to quickly target and observe these transient objects, combined with its sensitivity to faint sources and its spectrographic capabilities, makes it an ideal tool for studying future interstellar visitors. As detection methods improve and more of these objects are discovered, Webb will likely play an increasingly important role in characterizing them and revealing what other stellar systems are like. Part 13. Distant Supernovae and the Accelerating Universe. Webb has also joined the ongoing effort to understand dark energy, the mysterious force causing the universe's expansion to accelerate. In the late 1990s, two independent teams discovered that distant supernovae were fainter than expected, implying they were farther away than standard cosmological models predicted. This led to the realization that the universe's expansion wasn't just continuing since the Big Bang, but was actually speeding up, driven by some unknown form of energy that permeates all of space. This discovery revolutionized cosmology and earned a Nobel Prize, but it also raised profound questions. What is dark energy? Why does it have the specific strength it does? Has it been constant throughout cosmic history, or has it evolved over time? To answer these questions, astronomers need to measure the universe's expansion history as precisely as possible at different epochs. This requires observing supernovae at various distances, from relatively nearby to as far away as possible, and comparing their apparent brightnesses to determine how fast the universe was expanding at different times. Webb's infrared capability is particularly valuable for this work because distant supernovae have their light shifted into infrared wavelengths by cosmic expansion. The telescope has observed supernovae at redshifts, where Hubble struggled, extending the measurement of the universe's expansion rate to earlier cosmic times. These observations have begun to reveal whether dark energy's strength has remained constant over the universe's history, or whether it has changed. So far, the measurements are consistent with a cosmological constant, a form of dark energy that maintains the same strength everywhere and at all times. But the precision is gradually improving, and subtle variations, if they exist, may eventually be detected. Understanding dark energy is one of the most fundamental problems in physics. This makes up about 68% of all the energy in the universe, yet we don't know what it is. Webb's contributions to measuring the expansion history are helping to constrain theoretical models and narrow down the possibilities for what dark energy might be. Part 14. The Chemistry of Cosmic Evolution. Webb's spectroscopic capabilities have revealed not just the presence of various elements and molecules in cosmic objects, but also their detailed chemistry. This chemical information tells stories about where objects came from, how they formed, and how they evolved. In distant galaxies, Webb has detected the spectral signatures of elements like oxygen, carbon, nitrogen, and others. By measuring the abundances of these elements, astronomers can determine how much nuclear processing has occurred in previous generations of stars. Galaxies with high abundances of heavy elements have experienced significant star formation and supernova activity. Galaxies with lower abundances are chemically more primitive, perhaps containing gas that hasn't been as thoroughly processed by stars. In star-forming regions, Webb has detected complex organic molecules, the carbon-based compounds that are the building blocks of life as we know it. These molecules form in the gas and dust surrounding young stars, potentially becoming incorporated into forming planets. By cataloging which organic molecules are present in different star-forming environments, astronomers can understand the chemical inventory available when planetary systems form. In exoplanet atmospheres, Webb's spectroscopy has revealed not just simple molecules like water and carbon dioxide, but also more complex compounds. Some observations have detected clouds and hazes made of exotic materials unlike anything in Earth's atmosphere. Others have found evidence for chemical processes that don't occur naturally on Earth, but that may be common on planets with very different temperatures and pressures. By combining chemical observations across all these different scales, from galaxies to star-forming regions to planetary atmospheres, astronomers are building up a comprehensive picture of cosmic chemical evolution. They can trace how elements move from the Big Bang's primordial hydrogen and helium, through synthesis in stellar cores, distribution by supernova and stellar winds, incorporation into new generations of stars and planets, and formation into complex molecules that might eventually give rise to life. Part 15. Looking Forward. As remarkable as Webb's discoveries have been in its first 2.5 years of operation, they represent just the beginning of what the telescope will achieve. Webb was designed for a nominal mission lifetime of 5 years, with a goal of operating for 10 years or more. Barring any unexpected technical failures, the telescope should continue observing well into the 2030s, limited primarily by the depletion of propellant needed for maintaining its orbit and orientation. The observation programs planned for Webb's future include deep integrations that will push even farther back in cosmic time, searching for galaxies from the universe's first 100 million years. These observations may finally detect population 3 stars, the hypothetical first generation of stars made purely from Big Bang hydrogen and helium, if any examples still exist, or if their signatures can be detected in early galaxies. Webb will continue studying exoplanet atmospheres, building up a large sample that spans the full range of planet types, sizes, and orbital configurations. This catalog will help astronomers understand which kinds of planets can retain atmospheres, how atmospheres evolve over time, and ultimately whether any show convincing evidence of biological activity. The telescope will observe more supernovae, both nearby examples that can be studied in detail and distant ones that probe the universe's expansion history. It will study more star-forming regions, more galaxy clusters, more gravitational lenses. It will watch how astronomical objects change over time, catching transient events like stellar outbursts, asteroid impacts, and perhaps the tidal disruption of stars by supermassive black holes. As Webb accumulates more observation time, astronomers will be able to conduct studies that require data from multiple observations taken months or years apart. They'll track how objects move, how their brightness changes, how their properties evolve. This temporal dimension will add richness to our understanding that single snapshots can't provide. Webb's data archive, containing all the observations the telescope has made, is publicly available to astronomers worldwide. This means that scientists who didn't propose the original observations can still access the data and potentially make new discoveries. Many of Webb's most important findings will likely come not from the original observation programs, but from clever reanalyses of archival data, finding patterns and signals that weren't anticipated when the observations were planned. The telescope has already transformed our view of the universe, revealing it to be more dynamic, more complex, and in some ways more mysterious than we thought. Early galaxies formed faster and grew larger than models predicted. The epoch of Reionization was more chaotic and patchy. Stars and planets form in environments more chemically rich than we imagined. The universe's expansion history poses puzzles that challenge our theoretical frameworks. These discoveries don't represent failures of science, but rather its success. Science progresses not by confirming what we already believe, but by confronting us with observations that force us to revise and refine our understanding. Webb has given us data that demands new explanations, better theories, deeper questions. And, perhaps most importantly, Webb has reminded us of our place in the cosmic story. Every photon that enters the telescope's golden mirrors has traveled across space for millions or billions of years. These ancient messengers carry information about epochs when the universe was unimaginably different, when the first stars were igniting, when galaxies were colliding and merging, when the chemistry that would eventually give rise to life was being forged in stellar cores. We are part of this story, made of atoms synthesized in ancient stars, standing on a planet formed from the debris of stellar explosions, using instruments of incredible sophistication to look back across cosmic history and ask questions about our origins and our place in the universe. Webb hasn't just shown us distant galaxies and exotic phenomena. It's shown us ourselves, reflected in the light of deep time, closing reflection. So, as you drift now toward sleep, let your mind wander among the images Webb has captured. Picture those ancient galaxies, shining when the universe was young, their light traveling across billions of light years to reach us. Imagine the vast stellar nurseries where new stars are being born, where planets are coalescing from dust, where the raw materials of future life are being assembled. Think about the exoplanets orbiting distant suns, each one a world with its own story, its own weather, its own chemistry, perhaps even its own life. Consider the mysteries that remain, the nature of dark matter and dark energy. The question of whether life exists beyond Earth, the ultimate fate of the universe, whether it will expand forever or eventually collapse back on itself. The James Webb Space Telescope is helping us address these questions, but it's also revealing new questions we hadn't thought to ask. This is the gift that great telescopes provide. Not just answers, but deeper, richer questions. Not just knowledge, but wonder. Not just data, but perspective on our place in the grand cosmic story. Rest now, knowing that while you sleep, the telescope continues its patient vigil, gathering photons from the edges of space and time, slowly revealing secrets that the universe has held for billions of years. Tomorrow, next week, next year, there will be new discoveries, new images, new mysteries to contemplate. The universe is vast, ancient, and beautiful beyond measure. And we're privileged to live in a time when we can observe it with instruments like Webb, to ask profound questions, and sometimes find astonishing answers. If you've enjoyed this journey through Webb's discoveries, please consider subscribing to The Science Pillow, where we'll continue exploring the cosmos and the many mysteries it holds. And if you'd like to support the creation of more content like this, please hit the like button and share this with others who find wonder in the night, sky. Sweet dreams, fellow travelers through space and time. May your rest be peaceful, and may your dreams be filled with stars.